Hey, hello. Hey there, welcome to the second half of the sensation lecture for Gen Psych. We're going to get at these last two learning outcomes. I've actually added one, a new, and taken one from the previous video. We're going to talk about how we know we all see the same colors in this video, and then we're going to move into the tracking of visual information from the retina all the way on back to the brain. So let's start with this color question. Do you think you see the same colors that I do? I've got a different YouTube video to share with you to show you the answer to this question.
You might have heard that light is a kind of wave, and that the color of an object is related to the frequency of light waves it reflects. High-frequency light waves look violet, low-frequency light waves look red, and in-between frequencies look yellow, green, orange, and so on. You might call this idea physical color, because it says that color is a physical property of light itself. It's not dependent on human perception. And while this isn't wrong, it isn't quite the whole story either. For instance, you might have seen this picture before. As you can see, the region where the red and green lights overlap is yellow. When you think about it, this is pretty weird. Because light is a wave, two different frequencies shouldn't interact with each other at all. They should just coexist, like singers singing in harmony. So, in this yellow-looking region, two different kinds of light waves are present. One with a red frequency, and one with a green frequency. There's no yellow light present at all. So, how come this region, where the red and green lights mix, looks yellow to us? To understand this, you have to understand a little bit about biology, in particular, about how humans see color. Light perception happens in a paper-thin layer of cells, called the retina, that covers the back of your eyeball. In the retina, there are two different types of light-detecting cells, rods and cones. The rods are used for seeing in low light conditions, and there's only one kind of those. The cones, however, are a different story. There are three kinds of cone cells that roughly correspond to the colors red, green, and blue. When you see a color, each cone sends its own distinct signal to your brain. For example, suppose that yellow light, that is, real yellow light with a yellow frequency, is shining on your eye. You don't have a cone specifically for detecting yellow, but yellow is kinda close to green and also kinda close to red, so both the red and green cones get activated, and each sends a signal to your brain saying so. Of course, there's another way to activate the red cones and the green cones simultaneously, if both red light and green light are present at the same time. The point is, your brain receives the same signal regardless of whether you see light that has the yellow frequency or light that is a mixture of the green and red frequencies. That's why, for light, red plus green equals yellow. And how come you can't detect colors when it's dark? Well, the rod cells in your retina take over in low light conditions. You only have one kind of rod cell, and so there's only one type of signal that can get sent to your brain, light or no light. Having only one kind of light detector doesn't leave any room for seeing color. There are infinitely many different physical colors, but because we only have three kinds of cones, the brain can be tricked into thinking it's seeing any color by carefully adding together the right combination of just three colors, red, green, and blue. This property of human vision is really useful in the real world. For example, TV manufacturing. Instead of having to put infinitely many colors in your TV set to simulate the real world, TV manufacturers only have to put three, red, green, and blue, which is lucky for them, really.
Such a good video. So if I don't have it in this show anymore, the link will be below in the description, and I highly recommend you go check it out. It's a really excellent description of how the eye processes color information. The short version of this is that there are three different types of cone cells that roughly correspond to the light wave frequencies of red, green, and blue. And because you can combine red, green, and blue to create most of the rest of the colors that we could naturally see, you can create most of those colors, rather all of the colors, by combining red, green, and blue to different levels of intensity. So for example, if you send both red and green signals from your eyes to your brain reads it as yellow, even though your eyes technically saw red and green. The same as if you saw actual yellow out in the world. It looks exactly the same to us once it's recombined by the brain. The video maybe oversimplifies a little bit. It's not that the cones are tuned to colors, it's that they're tuned to wavelengths of light. That would maybe be the most accurate way to describe exactly what they do. We also seem to have higher level mental processes that compare one color to another to give us a more nuanced perception of color than we might even feel sensationally at all times. So there's a couple of extra things to be added to what is otherwise an excellent video to give you a pretty solid answer, I think, to, yeah, we all pretty much see the same colors because we all have the same rod cells, the same cone cells, and they're all tuned to the same light wavelengths. Again, we know all this because light exists as a wavelength. So you see the entire spectrum of light rays here. When you get to the visual spectrum of light wavelengths between 700 and 400 nanometers, you have the visible spectrum of light. Anything slower or faster moves into things like infrared radiation or ultraviolet radiation, X-rays, gamma rays, microwaves, radio waves. So our vision actually exists on the same spectrum as those that created the Hulk. Fun fact. Take that home to the bank with you. Definitely true. There's a feature of the wave that's not discussed here outside of the length, and that is the amplitude, or the height of it. That, in the case of light, determines brightness. So to compare this to sound, by the way, if you were looking at faster and faster wavelengths of sound, the pitch of the sound would be getting higher and higher. Whereas if you were looking at taller and taller amplitudes of sound waves, it would be getting louder and louder. One other thing you can learn from learning that cone cells are tuned to red, green, and blue wavelengths is how color blindness works. It's not, of course, the case that people totally can't distinguish something. What really goes on is that they, in an image like this, people with a red-green color blindness aren't perfectly able to distinguish these things from one another, especially as the colors get less bright and more gray. They start to look really, really similar. And the reason for that is that their retina lacks one or another type of cones. So you can imagine if you had very few cones that received the red wavelength, most things would look sort of green or gray. You wouldn't be able to distinguish between red and green in the same way. Technology has enabled vision researchers to do this feature, to do this transformation of images that we call band pass filtering, which has given us even more information about how we look at edges and how we look at specific lines in images and how we know things about the gist of images. And it turns out human vision is very specifically tuned to edges. We're looking for lines on stuff. They help us define almost everything we see. I mean, think about why do cartoons have outlines in them? They could just be different colors on different backgrounds, and we would still have, like, the shapes wouldn't change at all, but they're all outlines still. Why is that the case? And the reason is we're tuned really specifically to edges. So have a look. Do you recognize any of the faces on the screen here? How about now? Any idea who these four people are? You might be getting some of them. How about here, if I show you more just edge information? I think I figured out a second one. I think I got this one from this image, and I think I know who that is now. Let's see, a little more information. Oh yeah, we've got a lot more edges there. I think I've got all four. And at this point, you probably do until I reveal the final image of who those four folks are. But see how when all you have is fuzzy images, when all you have is essentially rod vision from either of these, you don't really have an easy time figuring out who's who. But as soon as I give you even really basic edge information, it can become really easy to identify who's who. If you're more curious about this, by the way, I recommend a visual cognition textbook. This is pretty high level, but it's super interesting, really well written vision text. That's where this example is from. At this point, you might be asking yourself, why does he keep talking about vision? I have 5 senses. Well, the first reason is we know the most about it. We've done a lot of research on vision. There's a lot of research on hearing as well, but I would call it a level more complicated and a level more difficult to understand. So for Gen Psych, it's nice to stick to vision. We've also, just as people in general, developed the most language around vision, by which I mean we can describe exactly what we're seeing and break it down to its basic components. And we don't really do that with smell and taste, unless you're at a really high level of scientific understanding of smell and taste. But even at high levels of smell and taste specifically, people still describe them essentially as comparisons and similes.
You gonna keep time?
I'm going to start with wine number 3. Wine number 3 is a clear white wine, and it's a little bit of a green apple skin.
Dana looked either completely sick or incredibly hungover, and I was really not sure which.
Have a white stone minerality to it. Notes of white grapefruit, sour gooseberry. Secondarily, it's driven by pyrazenic notes. Green grass, no oak, modern body, high acidity. This is a 1 to 3 year old wine from the old world, from a cool climate. Final conclusion 2013, Sauvignon Blanc, France. Loire Valley, Central Vineyard, Sancerre. Wine number 2 is a clear white wine of moderate plus intensity. Green and yellow apple skin, lemon juice. Secondarily, there's a radish, white pepper, no signs of oak. The wine's moderate in body, moderate plus acid. 2012, Grünweltliner, Austria, Wachau.
He hit 5 of 6 of the wines, so natural, so fluid. He basically read us our grid on the page as we just sort of circled everything.
2005, Cabernet Sauvignon blend from France, from Bordeaux, from their left bank, from Margaux. I'm done.
All right, Dan, thanks.
Thank you.
Well done, sir.
Thank you.
Good job.
Dana was definitely the tasting of the day.
Yeah.
So again, even at these really high levels of very careful smell and taste, in which they do come to some kind of upper level conclusion about it, they're still all described in simile and metaphor. He didn't talk about the compounds in those wines, he talked about the things that they smelled and tasted like. One last reason I talk about vision so much is that vision actually has very important social cues attached to it. In a study comparing a physician's eye contact with a patient to that patient's later score of their bedside manner, there's a major interaction between the amount of eye contact the physician makes and the length of time the physician spends with the patient. So if they spend a long amount of time, eye contact's not that important, but if they're only able to spend a short visit with that patient, if they make a lot of eye contact with the patient, they can get just as high a score as a doctor who stayed for a much longer period of time. So eye contact, hugely important in our trust in one another and in our opinions of how one another are acting. Another interesting finding is from a paper called Why Isn't the Trix Rabbit Looking at Me?, in which they calculated the height of a gaze of all the characters looking out from cereal boxes. And the idea here is that if the character is looking down, they're probably trying to make eye contact with a child who's going to be lower down in the aisle as they walk past, because they're going to be shorter than the adult. And lo and behold, if you look at the more child-directed cereal brands, first of all, there is more frequently a character included in them, and second of all, that character is more likely to be glancing downward because they're trying to make eye contact with the kid as they walk by. I'll give you one last topic to think about before I switch away from vision. Why can you read this? Which of our general vision learning outcomes from this video and the last does it pertain to? If you're having trouble writing an answer to that, think about whether this is a top-down process or a bottom-up process. And with that said, I will transition into just a couple of notes about some of our other senses. First, I want to introduce you to this interesting product. These are, I think they're called bone headphones. So check this out. The idea here is that these just vibrate on the outside of your ears, and that information is passed down and through into the bones in the ear and eventually into your brain. And in the meantime, your ear is actually still open. You're not putting the headphones in. So the reason these work is because that is how your ear works. It's the same reason that when your teeth collide, it sounds different than when somebody else does, right? If you clack your teeth inside your own head, it sounds very different from when I do it into the microphone. I won't do it more than I just did. Or think about like putting a pencil between your teeth and flicking it so it vibrates. You can kind of feel it go throughout your whole head. Or plugging your ears and talking. All of this is possible and is changed because sound waves are essentially vibrations that go through the auditory canal and vibrate the bones of the middle ear. So they vibrate all those bones you might remember from when you were little, the hammer and the anvil, and then they move the eardrum back and forth. Eventually, that information makes its way through the stirrup and into the cochlea. So they've drawn it partially uncoiled here, but it's essentially, it looks a lot like a seashell like it does in this upper image. And so inside the cochlea there's a membrane and there's hair cells and there's fluid, and all of those, as the hair cells are moved by the vibration, it gets translated into the membrane, which then sends information back through the auditory nerve to the temporal lobe. So the cochlea here is the source of transduction. It is the cochlea is to the ear as the retina is to the eye, essentially. It's the place where information moves from the way it's represented out in the world to electrochemistry that it can then send on to your brain. One fun finding I'll share with you from hearing outside of the bone headphones is that there's a sound shadow created by our head. So if you have somebody close their eyes and try to snap or clap around this, try this at home, it should be harder to locate the snap or the clap if the person is either in front of or behind the person with their eyes closed than if they're to the right or the left. Imagine this. So if I snapped from over here, this person would hear it first in their right ear and then sometime later in their left ear. And so we subconsciously use that information, that is the difference in time of the arrival of the sound at both ears, to figure out where it is. So if it arrives here and then arrives in the left ear much later, then we know it's probably directly off to the right. Whereas if the message arrives in this ear just barely before it arrives to the left, we might know it's more in a diagonal direction. But on the other hand, if you're behind somebody and you snap, your snap is going to hit both of their ears at the exact same time. So it's possible that it might be a little bit harder to identify exactly where that snap is coming from because you don't have the sound shadow to help yourself identify the location. I'll finish by talking a little bit about touch, particularly pain. So feelings of pain seem like they might possibly be objective. If pressing or cutting or burning damages your skin or your blood vessels or your bones, then it should hurt. And if two people have the same damage to their skin, then it should hurt them the same amount, right? No, pain is very subjective. It's a very interesting and active field of study. One such example was actually shown reasonably well on a medical TV show, believe it or not, and it's the reality of phantom limb pain, which is actually treated sometimes through a therapy type called mirror box therapy, which was shown on an episode of House.
Canada
So I'm
did
going to
not
go
send
ahead and
troops to
skip
fight
through
in
this.
Vietnam, you idiot.
I'm going to skip past that because I'm sure that would get pulled down if I left it on. But this clip is really cool. It actually shows pretty legit mirror box therapy, so check it out. That finishes this video, and the next one will cover the top-down side of processing in vision, that is perceptual set in many cases. We'll talk about how that can result in visual illusions. See you then.